My name is Elizabeth Henry. I'm the president of the Environmental League of Massachusetts, and together with Brad Campbell, president of the Conservation Law Foundation, we welcome you to what I hope will be an educational and thought-provoking 2 hours. This is being recorded, so we can share the link afterwards. Brad and I are grateful to Jane Hotchkiss and the team at Energy for the Common Good for their support and partnership. And we're also grateful to the teams at the Massachusetts Institute of Technology and Commonwealth Fusion Systems for sharing their time and expertise. Later in the program, we'll be joined by Congresswoman Lori Trahan, who's also joined by her fabulous district director, Emily Byrne. And we'll welcome a special guest, Rainer Bucas, to introduce her. Over to you, Brad.
So why are we here? We know the health of our planet and the future of humanity depend on creating carbon-free energy at an enormous scale. Renewable energy is booming, storage technologies are advancing, and we know that both of those have a massive role to play in decarbonizing our economy. But even the most bullish scenarios for deployment of renewable energy suggest it may not be enough to bring the globe to net zero emissions by mid-century. And current net zero pathways being developed by policymakers invariably seem to rely on dubious or potentially false solutions, reliance on nuclear plants long past their design life, or massive deployment of biomass with uncertain carbon implications. So we need to significantly scale up our deployment of renewables and storage, and in parallel, continue the research and investments needed to expand the climate solution set. In many people's minds, fusion still is in the realm of science fiction, conflated with nuclear fission and always seemingly 10 to 15 years away for the past 30 years. And it's true that fusion still faces many technological barriers to being viable, much less commercialized. But with those challenges aside, there have been exciting and significant advances in recent years. And if fusion were to succeed, it could generate abundant, safe, and nearly zero cost energy. Fusion is a very competitive arena with at least 27 funded companies globally and many universities and research institutions in the race to commercialize. Today, we've invited MIT and CFS because they are well established and in our backyard. We want to be clear that we're not endorsing or favoring any particular company or technology. We celebrate the diversity and breadth of the fusion industry, and we've asked MIT and CFS to speak both to their work as well as to the broader fusion landscape.
That's right. And this session has been about 2 years in gestation, hasn't it, Brad? We were going to meet at MIT and then it was waylaid by the pandemic, but we've been talking about doing this for a while. I think both ELM and CLF agree that fusion is a moonshot, but that the potential is too great to simply ignore, particularly by us here in New England. We are one of a handful of global hubs of fusion R&D. So we have been thinking for a while it would be really productive to convene our environment and environmental justice colleagues, business association friends, and policymakers to just learn about the current state of fusion, the technologies, the opportunities, the gaps, and the risks. Because in the years ahead, we're going to together need to be more equipped to comment on federal funding and regulatory considerations, and to look at the horizon to foresee some of the potential implications for issues like siting, transmission, environmental justice, in our regional innovation economy and our shared grid. So I'd like to welcome Jane Hotchkiss. She's the co-founder and president of Energy for the Common Good. Jane has done a lot to educate me and many others on fusion. Jane spent 30 years in energy, beginning in the late 80s, building markets for the renewable energy industry. You were the first renewable advocate at the Conservation Law Foundation, and in addition to that advocacy and policy and regulatory work, Jane developed a national field of anti-coal campaigns as the co-founder of the Clean Energy Task Force, and later as a climate consultant to PG&E on the Madison Wind Project. Jane has spoken really movingly to me about her worst fear, and you'd think that that fear would be that fusion would never hit its technical milestones, never become a competitive source of utility scale electricity in time to bend that arc of emissions. But Jane's worst fear is that it does, that we have some spectacular breakthrough and then we wait. We wait an excruciating decade or two to grind through everything that slows down any new clean energy technology from coming to market: regulation, siting, public acceptance. I reflect that the first offshore wind farm was built in Denmark in 1991, it was 30 years ago. And everyone who watched and waited for 3 decades till this fall's ribbon cutting at Vineyard Wind can empathize with this fear of change. It's our view that the urgency of the climate crisis demands that we, policymakers and advocates and stakeholders, be willing to undertake a learning journey that is parallel with fusion's development and not sequential. So before I turn it over to you, Jane, I want to remind folks that this is a meeting. It's not a webinar, and we hope that it can be interactive. We've budgeted time for some questions after each segment, and we'll use the chat function to collect them. Please make use of the chat function to share your reactions and raise your questions. We're committed to taking as many questions as we possibly can between now and when we wrap at 12. If we don't get to your question, someone from this group will follow up after the event. So welcome, Jane.
Thanks, Elizabeth. And I want to tip my hat and send out a great amount of applause to Brad and CLF and Elizabeth and ELM. This has been long in the making. And it is the first big fusion and environmental discussion of this magnitude led by leaders in the environmental community. And this is one of our dreams come true. So we're excited. As Elizabeth said, I'm the president of Energy for the Common Good. We are, at this point, Fusion's only strict advocate. We're a third party. We don't align with any one fusion company, but we are certainly promoting all of their advances, as well as Elizabeth also noted, are focused on our mission, which is to bring fusion to a world that's desperately waiting and excited to meet it, to use it, to put it, whether it is connected to grids or industrial processing heat, or even producing fuels for tomorrow's cars and trucks and perhaps airplanes, and we don't even know what comes next. Fusion is one of those breakthrough technologies, or actually I like to say energy sources, that can meet and partner with all of the renewable energies and clean energies that I've spent my 30 years in energy working to develop, and let them prosper, as well as meet the needs of many throughout the world that don't, at this point, have access to steady state, reliable power. And having just had the great privilege of speaking at the climate convention in Glasgow, I was really, really humbled to see the breadth of the world represented there, and looking to all for solutions going forward. With that, I have the incredible privilege of introducing one of my, well, I'm just a huge fan. He was one of the first people I met in Fusion, going on a decade ago. And he's somebody that I think everybody here will follow closely, not just today, but going forward. Dennis Whyte is a world-renowned scholar in physics, as the National Academy recognized with his leadership in promoting the report that indicated that fusion is real within the last year. Dennis is a recognized leader in the field of fusion research using magnetic confinement of plasmas for energy production on a faster and smaller and innovative path. Those are a lot of words that are very unfamiliar to most, and you will become more familiar as you listen to Dennis. What you should take away, though, is that he has led in an area of physics long studied, and he has boldly taken known technologies and brought them into a world that is now approaching compact fusion devices that will actually produce power versus research projects. So Dennis is a fellow of the American Physical Society with over 300 publications. He's the head of the Plasma Science and Fusion Lab at MIT, where he's also a beloved professor And I think you'll also recognize all of the themes of innovation and the need for speed and economic viability in fusion throughout all of his comments. He served on the panels, as I said, of the National Academies, the US government, the Royal Society. And it's also important to know that Dennis is a fellow Massachusetts resident now. He's got a wonderful wife and 2 daughters, and he's even a writer, producer, and I believe director, and perhaps even a member of the cast of a musical, The Pendant of Penzance, which he did all the while he was promoting, producing, and cultivating what is now one of the leading fusion companies, Commonwealth Fusion Systems, and pulling his team at PSFC together to build the core of the Spark project. So with that, I think I'll let Dennis cover all of his brilliance with his own words. Dennis?
Hi, thanks, Jane. Thanks for those kind words. I promise I'm not going to sing any of the comments on this. First of all, just
Please.
can you actually see my slides? The slide. Yep. Right. So thank you for that. So really want to talk about a little bit comment, to what Brad said. Fusion has always seemed like this long away, possible energy source. And I think, the reality is that has changed, and I'm going to explain about why that's changed. So first of all, what is fusion? So fusion is the process that powers stars like our own sun. It's literally the power source of the universe, because this is what all life in the universe relies on, because it comes from the power of stars. And in stars, what happens in the center of them is hydrogen fuses together into helium. This is a simplification, is basically what happens. This releases enormous amounts of energy, and the fuel of the sun, which is the big ball of hydrogen, lasts for billions of years. So commercial fusion systems, well, the idea is very simple. It will harness this energy to provide power to the world. And what it looks like is you basically fuse together 2 forms of hydrogen. It forms 2 other different particles. It actually changes the element. It changes it into helium and a free particle called a neutron. And this releases staggering amounts of energy, approximately something like 20 million times the amount of energy that you could get from a chemical reaction. This is why the fuel, you need very, very little fuel, and it lasts for a very long period of time. So fusion is often, and I understand the confusion is often confused with fission, but indeed it is actually the opposite of fission, which is the process that powers standard nuclear power plants right now. So at its heart, fission, the fundamentals of fission is that it requires heavy elements like uranium that are split into lighter elements to release and it releases energy in that process. The process is sustained with a chain reaction that can run away, and the resulting products have to be radioactive. These are the physics fundamentals of fission. Fusion is literally the opposite of fission. It takes the lightest elements, it combines them together, that's the word fusion, to form heavier elements, particularly helium. This releases large amounts of energy in the process as well too. That's the only thing that really makes them similar. The process is sustained not by a chain reaction, by heating, therefore it cannot run away, particularly on Earth. It just turns off. And the fusion reactions produce in the end helium, which is a harmless inert gas. So those are the fundamental physics differences of fission as compared to fusion. And then if you take all these and put them together, fusion has at its heart key advantages as a terrestrial energy source. So one is the fuel. The fuel comes because its forms of hydrogen is free and everywhere because it's just in water. It's carbon free and effectively inexhaustible. It will last for 100 million years or more. So that makes it a pretty attractive energy source. Second is that because it can basically be turned on anytime. You could sort of say this is like on-demand intense solar power because it's using the power of the sun, and it has very high power density. This means it has a very minimal environmental footprint about land use and so forth. Number 3, it is intrinsically safe. It is not engineered safe. So things like meltdowns and runaway reactions are physically impossible in fusion. And then finally, as I mentioned before, is the fundamental product you get out of this is helium, so you can blow up your kids' balloons for the for the birthday party, and you don't actually have long-lived waste products because it's not part of the fundamental process. So these are four very attractive things, of course, which about why fusion has been thought of in a sort of abstract way as a fundamentally and exciting new energy source. But it also requires special conditions actually for making fusion. As I said, in the universe, naturally fusion occurs in the center of stars. And the center of stars are very hot. This is what people mostly tend to focus on, is this middle aspect, is that it is very hot. Middle of our star is something like 15 to 20 million degrees Celsius. On Earth, we have to achieve the fuel to being at around 100 million degrees. So this sounds strange. Like this is the part that sounds like science fiction, that in fact it's at such high temperatures. But in fact, it requires more than just high temperatures. And this is akin to, as I said, this relies on heating itself. So it's akin to making a fireplace. So you think about making a fire, you need enough wood, you need to spark it, you need to get the temperature of the wood hot enough. And then you put it into a configuration where basically the burning logs keep the other logs burning, and you get a fire, and then you got a bonfire. Fusion is very similar. And so you take this, you get this fuel at 100 million degrees. You also have to have enough density of the fuel, but the density of the fuel is something like 100,000 times less dense than air. And this is an aspect of why it's intrinsically safe. There essentially is almost no fuel particles at any time. Like a power plant would have less than a gram of fuel in its fusion fuel at any given time. And then you put it into a configuration which has to do with containing the energy of this for about 1 second. And if you put these all three together, then it makes a star on Earth that, namely, it's heating itself and producing copious amounts of net energy. So how do you do this? So you can't have a physical container that holds 100 million degree fuel. So what you do is you basically make an insulated system that holds the fuel and holds the star at a distance without actually physically touching it. So we use magnetic fields are the primary way to do this. They're insulation for the hot charged particles, which is this medium called the plasma. This essentially replaces the gravitational force which stars use. And so this makes it more compact. So like insulating a house, you can keep something hot. You can think of it this way, by one of the ways is making the walls and making the other parts very, very large. Intuitively, you understand very large things stay hot for a longer period of time. The problem with that approach is that it costs a lot of money because you're building a large object. Or the other way to do it is you make better quality insulation. And the way to do this is with high magnetic field, because the gravitation, the magnetic force increases as the field increases and the quality of the insulation gets better. So the thing that you see on the right is a configuration of these so-called, with electromagnets. Essentially, it's a magnetic cage. And this is the best performing magnetic field geometry by far. And it has this particular shape, it's called a tokamak. We know these very well. We've built about 170 in the world, 3 at MIT, which are world-leading research devices themselves. And the physics of this tokamak is well understood. I will not bore you with all the details of that. But why don't we have commercial fusion yet? Well, because so most people think, well, fusion hasn't worked yet. Well, that's not really quite true. And also this 100 million degrees business sounds quite difficult. Well, it turns out this all comes down to making net energy. So in the end, what we do is like a fire, we get it hot, but then it has to make enough fusion power that the amount of fusion power that's coming out exceeds the amount of energy that we're providing to this fuel to keep it hot. So we call this capital Q. This is just simply the ratio of how much fusion power we're making divided by the heating power that we have to supply to it. So this obviously has to be significantly in excess of 1 in order to be a commercial power plant. But yet the things which sound like science fiction, and this is demonstrated on this plot over on the right, where the horizontal axis is the temperature, and 100 million degrees is where my thing is, where my mouse is. Whoops, sorry, where my mouse is right there. And then the other two parameters, the confinement and the density of the fuel on the vertical axis, we've gotten very close to actually demonstrating that we're making more fusion power out than we're making in. We've actually made up to 10 million watts of fusion power. We've created fusion reactions and things which exceed 100 million degrees on Earth stably as well too. So the blue dots that you see on this are the tokamak configuration. It has the highest demonstrated performance. A power plant needs Q above 10. So in fact, you would sort of imagine that you're getting up to this line right here. You can see on this plot, we're not very far away from. And the science of these blue dots, which are real experimental data points, we're right at the edge of making net energy. The problem is how to get there quickly to combat climate change and clean energy. So a few years ago, fusion energy had really stagnated and looked distant. So what happened? Well, the progress towards that goal, which is on this plot shown by this top yellow line, of getting to the point where we're making net energy, from the invention of the tokamak in the early 1970s through the span of about 25 years, was staggering progress. It had improved the performance by factors of 10 to 50,000 actually in this performance. Just amazing scientific achievement. But what happened was that actually at that point, starting around 2000, is that, and now we see this, is that the next step and the next dot on that point became very, very far out. This was not a science limitation. This became the limitation of the fact that the device, in this particular device, it's a device called ITER, which is a large scientific collaboration, became very large, expensive, had a long time duration, and was in a very complex project. So that was the reality of where we were. So we asked ourselves a question, was there another way? And starting around 2016, and Jane was part of those original conversations, and obviously my colleague who will discuss this afterwards, Bob Mumgard, we basically concocted a plan that took a look at this and figured out, could we go faster? And really, we broke this down into a simple axis, so that namely, the science of fusion is complex, but we had this really well-known thing called the tokamak. The problem is that its pathway had been very large and expensive devices, which didn't seem like it was going to be ever ready for combating climate change by mid-century. We also had other interesting aspects, which were the private sector fusion endeavor was starting to build up, and people were really saying, we absolutely must have fast, small, inexpensive things to develop. But the problem is that they had pretty significant physics hurdles to overcome. So we sort of asked the question, could we have something that has high confidence in the science, yet could be fast, small, and inexpensive? So here was this question mark, what we had asked. And the answer was yes. And it was based on a breakthrough opportunity that did not directly come from fusion, but actually came from another field. That it was namely how to make the electromagnets and make very strong magnetic fields. So as I pointed out before, we need very strong magnetic fields to provide good insulation. And to be able to do this, you need electromagnets, and electromagnets cannot consume large amounts of power. So you can make a science experiment like we did here at MIT, but it will not be an energy source because creating the magnetic cage will consume more power than it's actually you're getting from fusion. So we need so-called superconductors, and superconductors have limitations as to what magnetic field and operational considerations they can have. So what we found out and discovered was that there was a new pathway. And this new pathway was so-called HTS, high temperature superconductors, which basically opened up very much the ability to make much higher magnetic fields, improve the insulation. And then the idea was that what we could do was actually, but by the ability to make much stronger magnetic fields, improve the insulation, greatly reduce the size of the tokamaks based on known rules of science, and therefore speed up the pathway to fusion. So what does this look like graphically? So this is the same plot as I showed before, but now it's got some things on it to provide context. So the old pathway to fusion was really one of continually making things larger because they had basically run into the limit of the magnet technology. The right-hand side of this plot, which basically said that the science of this based on 25 years plus of tokamak science, if we can increase the magnetic field to these regions over here, we can shrink the sizes of these devices, and in particular, those that actually showed net energy for the first time will shrink by a factor of 40 based on the science of what we know, if we could actually achieve and essentially approximately double the magnetic field of the superconducting technology that was there. And over here to scale, you can see the ITER device. There was the device on the left that was built at MIT, and here's the device that is being constructed now in Devens, Massachusetts. These essentially have the same physics and performance mission, and you can see the vast difference in the size of these from one technological breakthrough. Wow, very compelling, because this brought a whole bunch of things into play: speed, commercialization, and so forth. But we also needed a new kind of model, and I think this is another part that was really critical to this. It wasn't just the idea that we had a great science idea, we had a great organizational idea. And what we came up with was a new model for research collaboration and tech transfer. We leveraged the enormous investment that we'd had from the government's sponsorship. But now we brought, with the announcement of last week, $2 billion. This is all private sector funded of what we were doing. We currently have about 240 people working on this across CFS and MIT. So what do we do with this? We actually created a Venn diagram, which overlapped the idea of a standard research university bringing forward the science. We coupled it very strongly to the private company, Commonwealth Fusion Systems. Bob is the CEO of that. And in the intersection of this, we had the things that were the development and the research which are needed to get going forward. So this basically brought together the best from both academic and startup worlds. We worked together. We did this with very rapid tech transfer, and we essentially accelerated through the valley of death as fast as possible. So a little bit of the history of this started, and we came public with this around 2018. This got off to a great start. We had immediately over 50 people working on this project. We got a lot of excitement. We got a lot of energy sector investment, which came in, and VC, Bob's going to talk more about that part of it. And part of this was because we also worked out a way that Spark and CFS were born at scale because they leveraged the existing MIT infrastructure and people in space. So this is a part of a coupling of what had been large amounts of investment in people talent and in space talent, about basically then turning it towards this idea, can we do more to address climate change on a more rapid timescale? So what did we do? Well, then we took the next 3 years, we garnered the resources, and we basically reinvented the center, of which I'm the director at MIT in this area. We took the talent that was there and we coupled it with the company. And so we took one of our largest experimental spaces at MIT, we cleared it out, and then we built a world-class and unique test stand to actually test this critical new technology, which was the magnet technology. You can see the space, which is in here. This is a little bit about fusion. You know, 3 guys in a garage are probably not going to solve fusion. It's hard tech, so to speak. And then we did it. We basically built and tested this revolutionary new magnet technology on the right timeline, with the idea that it was going to be passed, to the company, and Bob's going to talk about that. But it was fully representative of the device of the magnetic fields technology, which is needed in the device and the next scale tokamak. We doubled the magnetic field compared to the previous technology, and it was the largest magnet of its kind made in the world. We scaled up by a factor of basically 100 in the span of a couple of years, and it was a very exciting moment. On September 5th of this year, we actually successfully tested the magnet, and it passed all its tests. So what does this really mean practically? So, this is a part of the excitement that's coming in fusion right now. That this new technology really means that we have right in front of us the ability to go and actually see net energy from a fusion device on a very short time scale. And why was this? Well, it has to do with Spark, which is the device that we designed. Doubling the magnetic field compared to the old superconducting technology is truly a quantum leap. It's one of those moments as a technologist you get very excited by, because you see totally new opportunities in front of you. And why is this? Well, it's because, to get a little more technical, like the fusion power per unit volume scales like the magnetic field strength to the 4th power. Like, why are we so excited about something only doubling? It's actually a 16-fold improvement in performance to cost. We actually can access net energy gain in Spark. And really importantly, think about this, about the speed of which this will take. The size of the device compared to ITER, while it satisfies the same science mission, decreases by a factor of 40. So we needed this new technology, we developed it, and we deployed it. So what does this mean? So here comes Spark, which in parallel, we designed the physics around, which was based on the tokamak concept. In about a year ago, we published in full peer review. The science of this is completely open. We showed everyone what we were doing, 7 peer-reviewed papers that took all of that knowledge about the tokamak science and basically poured it in with the assumption that we'd be able to do this new technology work. So what does it do? This is important. Here you can see the size of the device. This makes 145 million watts of fusion power, but only about 12 billion watts to keep it hot, a net energy gain greater than 10. And when this turns on and works, this is the advent of a new era in energy, because it means now the power of stars is within our reach. So I'll conclude here by just making some, and I know that skips over a lot of details. You might have some questions about that, but my concluding remarks are the following. So it's really important. So as an academic, I want to do fusion research and bring, educate the next generation of people, but also think about bringing the science of fusion. It's a lofty goal. It's mythical in some sense, right? It's bringing the power of the universe here to Earth. That has to be exciting. But what has got me even more excited is the idea that this will be impactful in people's lives. And this is in front of us because the fusion energy industry, which MIT helped to launch through the start of CFS, but what's also going on across the board, and what was mentioned by Jane and Brad, has arrived. And what we're seeing in front of us is fusion development faster at a pace that no one had thought previously possible. Part of it is because it's coming through the private sector, but it's also coming from the reality of the science and technology breakthroughs which are in front of us. This will be a highly disruptive energy source. It's adaptable, it's scalable, it's carbon-free, and it's also an interesting energy source because it's based on knowledge, not really raw resources. So I'd say fusion is no longer just a curiosity-driven science project. When I came into the field, it was. This is also now a consideration of how we evolve an entire new industry that actually can get this up and going. I share Jane's concern. All of this is there. We make technology breakthroughs. Are we really thinking about the entire ecosystem that is required to actually deliver this new power source to the planet? So I'm proud that MIT has incubated and launched a key part of this with CFS as our partner. And we're going to continue to be a hub of building the fusion energy ecosystem. And I'll point out, so will New England actually be a hub of this as well too. So I'll conclude there. Thank you.
Dennis, thank you so much. And it's, I want to encourage those who haven't asked questions yet to throw some in, but I want to pull some questions out of the chat right now for you, Dennis, because it is many of the faces we can see or not see on this screen that will be part of bringing fusion to fruition as a power source as soon as we can possibly make it happen. And so we want to make sure everybody here has their questions answered so that they're satisfied that this is the technology that we know it is. The first question we got came in having to do with really the health and safety, but specifically, it came out of your first comment when you mentioned fusion not being able to run away. How do you turn it off? And how safe is that?
Yeah, right. So it's a bit counterintuitive because you hear something at 100 million degrees, and it's like, how can something be at 100 million degrees? So the way you have to look at it almost in the reverse lens. So the fusion reactions require these very high temperatures, not energies, temperature. And temperature means that it's basically, this is being isolated from everything else that's around it, because on Earth, everything else is at near room temperature or close enough to that. So what happens if there's a leak in the system? So the air comes in, immediately the fusion reactions stop because they're forced to return back down to room temperature. In fact, the fuel changes phase, it just turns back into a gas, and immediately within a fraction of a second, all fusion reactions stop. The other part of this is because it continues to make more fusion reactions simply by staying hot. It does not trigger the next reaction or anything like this. So when you put those things together, this means that any kind of external intrusion at all into the fusion fuel immediately stops all fusion. Literally, the device that like Spark that you're talking about in Devon's, a single human breath terminates all fusion reactions if it was actually incident on the fusion fuel.
Okay, and I'm going to jump in now, Dennis, because be careful what you ask for. I asked for questions, and now that I've got a whole lot of them, and I know our time is constrained. So yep. I want to. There are a number of technical questions which I'm going to read through quickly that maybe we can pull together. The question is, what is the timeline for testing 20 Tesla HTS magnets? And what kind of energy or fuel is needed to supply the 12 megawatts of heat?
So we already tested the HTS magnets at 20 Tesla. So that was already achieved. So they are, this gets more technical, but even though they're superconducting at 77 Kelvin, we actually subcooled them to be able to, so they operate more near 20 Kelvin. So that was already done. So they were operating at the temperature at which they will operate in Spark. What kind of energy fuel is needed to supply the 12? So the 12 megawatts of heat that we use in Spark comes from effectively FM radio, which is specially tailored. It's an electromagnetic wave, which then couples into the plasma and provides that heat. So it's intense FM radio.
So, and then I'll move over now to what a question on the regulatory pathway to approve a pilot plant. Does the NRC have to have the authority to license it, or is that a shared authority with the states? Obviously, we've all been involved in that. So
yeah, so I think Bob will have more details on that because CFS as the owner of Spark is actually the regulator. So at this point, though, Spark is Massachusetts' so-called agreement state, and NRC has already said, and so has the state. It will be regulated by the state, essentially as an accelerator, as a research facility would be, which is the appropriate way to do it.
And then we have a question. Are there any big scientific uncertainties as to the HTS magnets as they go into commercial testing, or are the risks more associated with the implementation?
Right, that's a great question. So it's primarily about implementation and execution at a larger scale, which is an interesting point of what I took some time to talk about the relationship between MIT and CFS. So this why we constructed it this way was that the tech transfer was, you could not be faster in this, because we understood that once you had basically figured out how the technology was going to be done, you needed to be able to hand it over to a commercialization entity as fast as possible. We literally worked alongside the commercialization entity because we can't do that as MIT. So CFS is now ramping up its capabilities to do that at a commercial scale. Is the optimization of the magnet technology done? No, and we're going to continue doing that optimization. But the biggest hurdles have been overcome.
And then we also have a question on how much hydrogen do you contemplate being used for this energy source, and concerns about the amount of hydrogen, for instance, needed in our atmosphere. Do we know enough about the way in which hydrogen functions, et cetera?
Right. So this goes back to fusion's fundamental attraction as an energy source. You cannot. This uses extremely small fractions of the heavier form of hydrogen that comes out of water. By how small do I mean this? So, since we're in New England, I'll use my New England anecdote for this. So if you take the top inch of water on Boston Harbor and you remove 1/6000th of the hydrogen in that 1 inch of water, and you use it in the fusion device like I showed, that provides enough electricity for Boston for 50 years. So you basically cannot run out. Yeah. So so it is not. So this is the difference of using it's not using hydrogen as a chemical source or like in a fuel cell. It's because we're changing the hydrogen into helium. This is why it releases 20 million times more energy in that process. That's why it works that way. Yeah.
And this is a question that gets at one of the reasons that we look to fusion as ECG in the beginning. And I'm sure many on the call or the Zoom are thinking about it, which is what amount of land is required for a practical installation?
Yeah, very.
In other words, how would we use this power plant, and how much space does it take?
Yeah, right. So this sounds very exotic, but in the end, actually, the kind of power plant that it makes is rather prosaic. That object that I showed of would have a very small land footprint, just because of the high amounts of power that it makes per unit size. So that's I guess that's really the answer. And you can take a look at the Devon site where a real thing is being built, and that will give you an indication. It's being built in an industrial park in the suburbs of Boston. That's the kind of footprint it will have. And sorry, what was the
Now,
next question, Jane? I think it was how you actually extract the energy.
well, there's how you extract the energy, but there's also a question about the nuclear waste implications, which
Okay.
I know is something we're going to get into. So
Yeah, so let me, actually, they're coupled, those questions, so let me answer them. So in the end, right, so this, you know, the exotic part of this, it sounds like, is making this 100 million degree fuel and so forth. But as I said, it actually has to be by design completely decoupled from terrestrial anything. So it doesn't even really know it's on Earth. It's in a vacuum. It's isolated by the strong magnetic field. So what is the fusion energy? The fusion energy is actually in the speed or the energy of the products that are made by the fusion reaction itself. So what you do is 80% of that energy in particular is in an uncharged particle. It leaves the magnetic cage. So what we do is we have something called a blanket, which is like wrapping a blanket around this special fusion fuel, which is made out of sort of more ordinary engineered materials. And that captures, it converts that energy into heat. And so that heat is then what you use. So if you just draw a circle around, you know, what you think of the magnetic cage or something like this, in the end, what's pumping out of this is just staggering amounts of heat, which you can use to make electricity. As Jane commented, you can use it for other things like industrial processing. It is an energy source at its heart. It's a fundamentally new energy source. So then the comment to that, so our design and our research in particular has really worked hard at also, so as I said, the fusion reaction itself does not produce a nuclear waste because it produces inert helium. As these particles go out, they can interact with the engineered materials around it, and they temporarily activate those materials. This is similar to what happens, for example, like in hospital, like in things like proton, you know, beam therapy for cancer. Like the objects just are nearby temporarily get activated. So we have a design where the great majority of the materials that interact do not get activated past like a day or two. So that's really quite attractive. And then the other part is that the amount of this is the other parts of the engineered components have a very, very small volume, and that's one of the active points of research right now, is that we can sort of engineer our way out of that problem because we can pick components that actually do not act. So what am I talking about here is that they're activated materials for orders of years, not thousands of years.
and that's an important point. Again, the half-life is, you know, under 100 years. So we're talking about, and
oh,
you know, actually
even less than that if you're clever about the engineering of it. This is where it differs from fission in the sense that in fission you can't avoid it because it's a fundamental part of the process. In fusion, like I said, you can engineer your way to significantly more compatible solutions with this. So it's just a vastly different profile than anything like that. Yeah.
And so I know there are a lot of questions here, and I know some of them will probably be redirected later at for Bob when he describes and discusses CFS coming up next. I want to thank everybody, and you in particular, Dennis. And I also want to remind everybody who's watching and listening and a part of this, that we're talking about one of the many fusion technologies that are under development. I know there are a couple other companies on this line right now, and their fusion devices are going to have a slightly different approach, and therefore they're going to answer some of these questions a little bit differently. That's one of the beautiful parts about fusion, is that there are going to be a number of different approaches that will accomplish different sized and different configurations of our energy needs. Thanks, Dennis.
Yeah, and I completely agree with that statement. That is a physics true statement, by the way, because I can't talk into detail about this, but this is in fact the reality of fusion. There's many ways to get there. We hope our way is fast, but of course we encourage all ways to get there. All of this is good. Yeah, so thank you very much, Jane. Yeah.
I think that
Terrific.
takes it to you, Elizabeth.
Dennis, that was extraordinary. Thank you so much. And thank you, Jane. Now I'd like to turn it over to Bob Mumgard. He's co-founder and CEO of Commonwealth Fusion Systems. Bob is responsible for the strategic vision and direction of the company. He's grown CFS to over 175 employees and raised over $2 billion from private investors, including just closing what I think is a pretty eye-popping $1.8 billion Series B round. Bob's overseeing the construction underway on a fusion campus in Devens, Massachusetts, which I hope you speak to briefly, Bob. Bob did his PhD work at MIT, contributing to the design of several small superconducting tokamaks and a variety of physics missions using high temperature superconductors. And you've also thought a lot about entrepreneurship, risk management. You were an MIT fellow as well, thinking through some of these path to market issues. So Bob has a PhD in applied plasma physics and a master's in nuclear engineering from MIT and a double bachelor's in mechanical engineering and engineering physics from the University of Nebraska. So Bob is going to take us through an outline of what he sees as the road to commercializing fission. Welcome.
Great, thank you so much. It's so exciting to be here. I really hope this is the beginning of the conversation. I'm going to start with sort of zooming way out. So, I think everyone here has played the wedge game, right? Wedge game is you look at what we simultaneously have to balance two competing needs. One, we need to decarbonize, like the world has to decarbonize. But two, we also need energy, and there's people that don't have energy today that deserve to have more of it. And when you start to look at what the scale of that problem is, this is just electricity worldwide, which is only about a third of the energy used today. You, of course, get big graphs with big numbers. Each of these units here is trillions of dollars. And in the future, we need to build a wedge out of zero carbon energy that is really big. We hope this wedge comes from as many technologies as possible because it is so big. This is like $80 trillion of infrastructure turnover and new build just for electricity worldwide. So like as many options we have on the table, we need. And that's really a motivating force for everyone that's involved in CFS and the other fusion companies that are commercializing is fundamentally we have to get carbon out of the energy system and also grow the energy system. And we don't have all the technologies to do it today on a silver bullet. There's no silver bullet out of this. So if you start to ask questions like, what do these wedges look like in terms of like deployment, like a commercialization plan? You can play games like this. This is a log plot. So each of these is a factor of 10 versus time. This is a deployment curve. This is historical deployment curves for other energy technologies. This is what that wedge was. I haven't picked a technology. I've just said, okay, there's a wedge out there, a combination of technologies. This curve has three defining features. One, it needs to start as soon as possible. But of course, if we already had all the technologies today, you'd start it today. But we're still developing some of them, including fusion. And so if you're too late, you miss it. And the atmosphere sets a timeline that says that you got to start like in the 30s. You cannot start, you'd like to start in the 20s, but you got to start at least in the early 30s. The other thing about such a curve is it's steep. It's very steep. What does that mean? It means it has to be very, very high growth. It has to be replicable. You have to have the ability to make many of these things and accelerate as you go. So that means you can't have barriers like land use or material inputs or things that slow growth. How steep? Well, fortunately, like solar and wind have been pretty steep. And fission, historically, was also pretty steep. So we know if you can manufacture energy production technologies, you can make steep growth curves. That gives us hope. Third, it cannot plateau. If you plateau 1 unit down on this chart, you are a 10% solution. And a 10% solution, we need a 100% solution for decarbonization. It's net zero, not net 90, So fission plateaued because it has inherent limitations. These are the accidents that happen in fission. Wind and solar, we don't know when they will plateau, but there is worry that they will plateau without some other technologies and certainly in some parts of geographies. So the ideal technology means that you want something that is as soon as possible, obviously zero emissions, quickly replicable, power dense, that you manufacture, that doesn't use a lot of land, that doesn't use a lot of materials, that can use existing supply chains, existing finance and procurement channels, and existing infrastructure. That's what that your best shot at making this curve happen. And so that's a very commercial mindset of like, okay, if we make a technology, it needs to have these attributes and it will find the market and the market can then help it scale just like we saw with wind and solar and continue to see. Fusion fits so many of those attributes. So from a commercialization standpoint, it has this advantage that it's a power plant similar to power plants that we've built in the past, in that it's an engineered product that we build that is like the size of a coal power plant or a natural gas power plant that makes hundreds of megawatts of electricity, many more of that of heat, that you can then plug into an existing grid, an existing site. Imagine if you showed up at a site that was burning coal and you stopped burning coal and you put a different type of boiler there that was fusion. And you no longer have the coal trains, you no longer have the particulates, and you no longer have the carbon. The unique part about fusion, though, is that at the center of it, as Dennis talked about, the machine creates conditions that are inside stars. And those conditions we have not yet created on Earth, but we're, as Dennis talked about, close. And we have a pretty idea what these machines look like. So inside here, you have the conditions that create the fusion reactions. The fusion reactions produce fundamentally heat. That heat heats up the surroundings. Then you pull that heat off and you have a dispatchable, meaning you can turn it on and off, source of heat without any of the proliferation of uranium or plutonium, without any chain reaction, and without the long-lived nuclear waste. You have to manage various parts of this. This is an industrial facility, like this industry would be an industrial industry. But it's an attractive industry because of it reuses parts that we already know how to do in the existing energy infrastructure. Additionally, that source of heat could power lots of things. So when you start to think about what it takes to decarbonize the global infrastructure, it's not just about electricity. There are very difficult to decarbonize sectors. There are things that we're going to need liquid fuels for, or hydrogen fuels for, that we have to have places to make those fuels. The JFK airport in New York is 8 gigawatts of energy of jet fuel. Like that's like 8 nuclear reactors of jet fuel that go through that airport. It's a lot. So we have to be able to decarbonize all these sectors. And so having more energy sources that match industrial energy use is an important part of the equation. And fusion fundamentally does that. It can power hydrogen or desalination, or it can power direct air capture for carbon. And so we think it could fit into multiple places. Of course, how do we get there? The first thing is, it's as many good approaches as possible we need to do. So right now in fusion, there's a couple of different types of entities that are working in it. And one, Dennis talked about ITER. The worldwide scientific community has worked in fusion for a long time, and they're building a machine in the south of France. This is ITER. And it's sort of a multi-tens of billions of dollars statement of conviction that fusion is scientifically doable and worth doing. And that's a continuation of the work that happens at MIT and National Lab. There's also 27 fusion companies. They're trying other concepts. And so we're at the beginning of a really interesting ecosystem of multiple ways to get there with multiple entities, all using a base of science and engineering that's been laid down by government research, all trying to solve a problem that is a very big problem that multiple solutions are going to be able to work in that problem, and all trying to go as fast as possible. And so that's why we've brought together, this broad set of players. And importantly in this, we have to, from the beginning, get this industry set up right? We don't want to make the mistakes that we've made in the past, the mistakes of a serial process, of this defining the technology before having conversations with stakeholders, before getting everyone on the same page about what understanding is, and really listening to concerns. Because that growth curve I showed you before, in order to build a steep one that doesn't plateau, it's going to affect lots of people. And we want to understand those effects and bring them on board so that we can actually make curves like that work. That's true of fusion. It's also true of any other energy technology that we want to deploy. And so we've started to do that when we built CFS. So CFS today is about 175 people. And, we've gone out and tried to build a diverse team that, doesn't come from backgrounds in fusion. They come from backgrounds all over other types of technologies, because anything that we're going to do that looks like those growth curves means they're going to have to pull from lots of places. And we've worked closely with labs and universities. We publish what we what we come up with, and we invite people in, tour, invite people in to understand the technology. And where we are now is, as Dennis talked about, we have a magnet. Magnet works. That was the key thing we needed to do to understand what the next step was going to be. And now we're building that next step. And this is the Spark machine, which is similar to ITER. And that's also important because it means you can go and see these technologies. There's 150 tokamaks in the world. We can go and see them. We can have people go into their regional areas and go see the technologies that are at places like the national labs and universities. What we're doing is, in Massachusetts, is we're building Spark. And we're building that at a campus in Devens. And this has been a very rewarding exercise to go out and bring the communities around this facility together and say, hey, what do you think about hosting a new energy technology? What are your concerns? How can we get this right? And really having that conversation. We were able to have that conversation actually in multiple places around the country simultaneously to find the right fit. And Massachusetts, we knew, was always going to be a place that leans forward, thinks about things deeply, brings lots of people together. And that turned out to be the best place to build this. And so on the left is the actual campus that we're currently under construction. All of this is under construction. And this right here is the Spark facility. And in the middle is the tokamak, and it's very similar to the facility at MIT. And it's an industrial type facility, but made out of buildings that are like normal buildings. And it will, in 2025, turn on as a net energy fusion machine. Here it is under construction. So the basement is right here. And so this will be about 400 people at this site manufacturing things. And we've made it purposefully to be a place to come learn about the technology, learn about what fusion will be, and be open, inviting, and sit in a natural environment up next to the neighborhood, the regional area in Devens. After that, we'll build ARC. We don't know where we're going to build this yet, but we're starting to think about designing it, and we're starting to think about what all the implications and how to make the trade-offs that Dennis alluded to in terms of the attributes of this machine, its legacy, how it operates, where we can cite it, what it all. How it interacts with the policy and regulation. And so we're very, very interested in hearing those viewpoints and having those discussions. And that's part of our long-term plan. And we hope to actually start that ARC facility in 2025, 2026, after we demonstrate an energy in Spark, which is being constructed now, which will turn on in 2025. And so with that, I'm very excited to be here and have the discussion.
Thank you, Bob. We have a lot of questions about the technology, and I want to start with one that's kind of an overarching question, which is, a generation ago, we were told that nuclear fission energy was going to be too cheap to meter, and and like so many things that are sound too good to be true, there's a lot of what we're hearing today that just sounds too good to be true. What are some of the downsides of the technology? What are some of the criticisms that are going to be leveled at it?
Yeah, it's great question. I think first, in terms of mindset, so like every once in a while, something does happen that really does seem like it's crazy and too good to be true, like flight or like the steam engine, right? Like those, that just because we've had technologies not live up in the past doesn't mean that we should automatically assume things won't live up. So I always like to frame people that progress actually does occur. The other part of this is for this particular technology, what we're trading off is we're getting a system that is more complex. This is more complex than building a solar panel farm, right? But it's more compact. It means it's not going to be, it's never going to be too cheap to meter. It's a capital intensive thing. You have to build a piece of equipment, but the piece of equipment you're building is fundamentally different in its land use. It's fundamentally different than fission in the size of the downside. So fission has a very, very, very low probability of downside, and we argue about whether that's acceptable or not, but the size of the downside is large. It can be regional, and it can be intergenerational. In fusion, people haven't, from the fundamental process, the fact that there's no chain reaction, there's no plutonium uranium, there's no transuranics, there's no long-lived nuclear waste as part of the fuel cycle, means that you don't have these large, long-lived downsides, even if they're low probability. They're zero probability. On the site, though, you do have to manage an industrial facility that does produce some radiation when it runs, the same way that X-rays produce radiation when it runs. You can turn off a lot of that radiation, but you do end up with some materials that you do have to keep track of. Those are materials that are commercially exchanged today in terms of low level of waste, and they're not biologically active, but you do have to keep track of them. But you get to make some decisions about how to do all that. And those decisions come with trade-offs. And that's one of the reasons we're here today, so that we can get all the voices in the room when we make those trade-offs.
We have a lot of questions about waste, and it's easy to say not much waste or very low levels, et cetera, et cetera. But can you put that in perspective? Because clearly there's a lot of public concern about radioactive waste. It's one of the biggest obstacles to any further deployment of nuclear fission technology. And I think it's really important to put that in scale based on the questions we have.
Yeah, so two different types of scale, size and time. So what we're talking about here is things that last for, a decade. So things you have to keep track of for a decade. That's very different than 10,000 years. So and in fact, like, we keep track of industrial stuff for a decade all the time, right? That's something that is at the scale that you can regulate. That's something that's the scale that you can be responsible about, because you not have to worry about what happens geological timeframes or disruptions of society timeframes, which is really what a lot of people worry about in fission waste. The other thing is scale, and you get to make decisions about that. What we're talking about here is a system that produces, at the end of it, the piece that is the part that gets the most exposed to the plasma. That's the piece that becomes activated. That's a few cubic meters. So you can imagine that compared to, say, the amount of carbon an equivalent amount of system would have produced differs by about a factor of 1 million. So this is very, very different than both fission and the other types of waste that we get out of energy systems. Or you can even think about it, at the time scale and waste impact of, say, a wind turbine or a solar panel, which have heavy atoms in them that you worry about getting into the environment. They're not radioactive, but they're still very, hazardous.
Well, question about heat. What percentage of the heat that's generated in the fusion reaction is liberated into the environment, and how does that compare to traditional technologies like nuclear fission, gas, and coal? Yeah,
great question. So you get to make some choices about that. They're engineering choices about how complicated you make your say your steam turbine versus other ways to generate electricity, what the thermal efficiency of those systems are. So like nuclear is fairly low thermal efficiency. Fusion, from the studies that have been done, look like they have thermal efficiencies that could be similar to advanced gas cycles, which is exciting because it means that it's less. But you're still, somewhere on the order of like half the heat is going to have to be put into the environment, as any thermal system would have to do. But you're going to make choices about how you do that. For instance, there's, we've looked at doing it in a dry cycle. So it's not using water. It's not putting it into the waterways, things that we've learned from the past on thermal systems, how to apply those technologies.
What are some of the things that we have a lot of environmental advocates and policymakers on the line today, and where should their focus be when it comes to the prospect of this new technology coming online?
Yeah, so Congresswoman Trahan, I hope, is going to talk about some of the initiatives that are happening at the federal level, but I'd put it into two buckets. One, there's just an element of getting educated so that we can engage, right? That is a really important part of this part. And I don't want to, and it doesn't actually show up in any policy initiative beyond maybe making sure that when we're talking about clean energy technologies, we're talking about carbon-free technologies, we put fusion in, even though it's not here today, into things so that we have a level playing field and people trigger and think, oh yeah, let's make sure that we don't preclude options that we might want to use. So from a policy standpoint, there's a simple education, raising awareness, and making sure it's included in the broad-based policies that help everybody. Then there's some targeted policies, though, that are also really good. Targeted policies around what is the appropriate regulatory structure now and in the future, policies around what is the appropriate R&D structure at the incentives and federal level. How do we bring the pipeline of students and supporting technologies along with us? those types of things are all interesting. And some of that I hope we touched on next.
One of the lessons of the nuclear fission experience has been that technologies that have high capital costs, high operating costs, wind up producing electricity that's not economic, can't reach parity with other technologies. And so Davin asks, what provides the confidence that the capital costs and operational costs for a fusion power plant will lead to economically competitive electricity?
Yeah, so the one way you can think about it is in terms of order of magnitude of stuff. So a fusion plant, that fusion arc plant I just showed, that fusion arc plant, the weight of the stuff is the size and weight of the stuff is similar to the size and weight of an offshore wind turbine. But it makes 20 times more energy per unit time than that offshore wind turbine. And so that gives you a sense of, if it's made out of the same things, which it is, steel and concrete and things, and it's the same amount of stuff, which it is, and it makes more energy, it should be cost effective. So from a gut check standpoint, you have a reason to believe there. But more importantly than just gut check, that's one of the reasons we are building Spark, so that we come out of this with receipts, so that we know what it costs, so we know where the levers are to make it the most cost effective technology. And that's something you really only get by building.
We have a grid savvy question, which is this is fusion a technology that can be fast ramping and come on and off rapidly, or should we think of it more as a base load type of technology?
Yeah, so the inherent technology of fusion means that it can be fast ramping. It can be ramping, it's basically ramps on the time scale of like a gas plant for the same reasons in terms of the thermal load on the components. And so that means it could be used as a peaker or as a ramper. But then at the other side of the equation, it's a zero fuel cost, but capital cost thing, which means the economic incentive is to run it as much as you can. And so it can fill both roles, and you can actually build systems that allow it to fill both roles by, say, putting on more thermal storage, things like that, to adapt it to the market conditions, depending on, let's say, the penetration of renewables, or what are the users in that market and how variable are the demands, which makes it very flexible.
You just closed what Elizabeth described, I think aptly, as a eye-popping $1.8 billion funding round. What does that buy? What are you hoping those resources can achieve in the coming years? Yeah,
so the first thing is, and I showed you a picture of a construction site. So we started that construction site before we had all the money, because what we care about is how do we decarbonize as fast as possible. And so we're able to get going, even though the future was a bit uncertain. Glad the people that were building that are very happy that we closed the funding round. That funding round will enable us to build and run Spark. So the first thing we get is we get a operating fusion facility at net energy, so heat out more than the heat used to heat it, and all the subsystems that feed that, all at a level that is very close to what a power plant is. But it's not a power plant, it's a step on the way. The other piece of the funding that gets us set up to build the actual ARC power plant in terms of our manufacturing capability, but also in terms of the design and the R&D on some of these subsystems that we're talking about, that are things like making decisions on what are the materials and how does it impact the legacy of the plant versus the performance of the plant. We get to learn some of that in parallel to Spark, and hopefully working with partners in the public programs as well, across a wide national push in fusion that we're seeing emerge.
Winston asks, so at the end of the day, this is a thermal power plant, correct? Could this be used to power a district steam system like a combined heat and power plant?
Yep, exactly. At the end of the day, it's a dispatchable, low marginal cost, zero carbon source of heat.
And how many of fusion units or individual reactors would be needed to power a state like Massachusetts?
That's a great question. So the ARC system is about 200 megawatts electric. And what does that mean in sort of terms we use today? So that's a small gas turbine. So that would be the low end of a gas plant. A few ARCs would be what Plymouth was, and like 10 ARCs would be almost a little less than 10. Like 5 ARCs would be what Seabrook is. And so it's in the range of not something that is small that you're going to put, in your every neighborhood, but also not something that is a giant mega project. And so that's one of the advantages. And you could site them together. You could repower existing coal plants, for instance, like about one arc would fit a decommissioning coal plant. In the U.S., that's not so important, but it's pretty important in places like India and developing countries where they're still building coal plants, and you want to transition those in the near term to be not fossil. So we factor that into when we think about how to build these, what the sizing should be.
And what do you see as the biggest remaining challenges in bringing Spark online? And what do you think the biggest risks are along that critical pathway?
Yeah, so there's always challenges in building any complex project. I think anyone who's been involved in projects understands that challenge of, the more integrated it is, the bigger it is, the more people involved, the more challenging it gets. And so Spark is at a scale that's a doable scale. It's not ITER, but it's also not just like building a house. And so we have to do that well, and that's an execution challenge. Then past that, our challenges, we're really thinking more and more about, okay, what are the ecosystem building challenges that we need to face? So it's one of the reasons we're here today, and how can we tackle that so that in the future we can use Spark as an example that was done well for the next stage for ARCs and build up a fusion movement.
David Beckman asks, is tritium breeding and separation included in the energy costs for break-even calculations?
Yeah, it's a great question. So the way that we think about fusion, the way that fusion people think about fusion in general is, one, the really novel key thing here that hasn't been done is actually making a plasma that generates energy. And that's when we talk about net energy and we talk about Q, that's what everyone's always talking about, is the plasma itself. Once you have that, you need to have that be high enough that you can cover all your recirculating power losses. People don't usually talk about like the Q of a coal plant, but the Q of a coal plant is pretty high. It's like there's still a pilot flame in a coal plant that's putting energy to keep the coal burning. And generally, if you can get a Q of plasma above about 4 or 5 in a tokamak, then you can start to produce net electric, meaning the plant is a source of revenue, a source of energy into the grid at that point. And so Spark will put us into that regime, even though we won't actually convert it all to electricity. But of course, we've been converting heat to electricity since Edison.
There are a lot of communities, a lot of environmental advocates who have a fairly dim view of the Nuclear Regulatory Commission as a regulatory body, particularly in terms of its responsiveness to communities, its responsiveness to states, the seriousness with which it takes safety concerns. Do you or does the industry have a view about how this, putting aside the pilot plant initially, do you have a view about how this technology should be regulated over the long term?
Yeah, so the Fusion Industry Association, has a active government and regulatory function and convening function there. Not just the companies that are developing, but also companies that are affiliated, energy companies, suppliers, legal, all talking about these things and engaging with the states and the NRC. It's the position of the FAA and of CFS that, what we need to do is we don't want to get ourselves too hamstrung on things that we don't know enough about yet. So let's get some experiments out there. Let's try things. Let's see what works. Let's see what these things look like out in the community and what the community cares about. And the best way to do that is to use the states as sandboxes, and Massachusetts, which already regulates Dr. CMOD tokamak at MIT, but also regulates other types of accelerators at the leading hospitals. They're taking a lead for the Spark machine. There's Wisconsin is also doing something similar for a facility in Wisconsin. California is doing something for a facility there, which we think is the right way to get started. Long term, we'll have to see where these technologies go and see where the concerns are. I'd say in general, the U.S. is starting to think about that. Canada's been more advanced thinking about that, and the U.K. is the most advanced thinking.
So in terms of the pilot plant narrowly, what are, as Ann Weeks asked, what are the local and state approvals that you need, and which ones do you have?
Yeah, so for Spark, there was a compliance with the Environmental Protection Agency, and MEPA. So we went through that process for the Spark machine, and because it's at Devens, which is has an important history in the environmental and MEPA cleanup and things like that. A lot of the groundwork was already laid because of the use of the Devens facility and what they've done there already, and done a great job there cleaning that up. And so we were able to build on that. So we went through that process. There's, of course, was public hearings and community process on the permits for the actual buildings of the things. In addition, there was a lot of outreach on the ground of local groups, and that continues and is going to continue to ramp up. And so we have the permits we need to build it. We still will need to work a little bit on some of the operating procedures for how to operate it. That's still in discussions with the health part of Massachusetts, the Massachusetts Radiation Protection Group, which is a great group in the health side. And so those will happen over the next couple of years. And the key here is like how to have a continuing dialogue.
David Turnbull asks, what opportunities are there for interested and concerned individuals to participate in Fission investment? Yeah,
that's a good question. So, right now the Fission companies, they're almost all of them. I think all of them are venture backed. So that means they're backed by high risk investors who understand the risk they're getting involved with. In the same way that a lot of investors overlap with people invest in new types of rocket technology or new types of biotechnology or drug discovery. So that's where it is now in terms of investment. We'll see how it evolves over time. But it is such a specialized technology that the risk profile is fairly high from an investment standpoint, and best suited to the sort of institutional investors at this stage.
And what's the biggest challenge right in front of you in terms of as you build this?
Yeah, so right now we're it's people. So like before, I'd say 5 years ago there was a deficit of belief that it could be done, and there was then a deficit of money. Now it's a deficit of people. So this is a really exciting technology. So it's able to attract a lot of people, but you have to bring them on board and teach them about fusion. So it's been fun to teach people that build submarines and people that build bioreactors for vaccines, all about fusion systems. And we'll have to continue to do that. And why it's so important to have places like MIT that produce new graduates, and why it's so important to be at a place like Eastern Massachusetts that's a hub of thinking of engineering and innovation across lots of sectors. And so that's where we're spending a lot of our effort. Because without people on board, whether that's the staff or the collaborators or the neighbors, you're not going to get a technology to solve climate change.
And one last question. How is heat generated at 100 million degrees Celsius safely and sustainably transferred from the tokamak to processes needing heat in the hundreds of degrees, such as steam generation for power?
Yeah, so it's about insulation. So you probably don't think about this, but like inside your incandescent light bulb, that filament is very, 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 very hot, but it's very well insulated. And so you can put your hands on the outside of the bulb for a little bit. And it's the same thing happens inside a fusion machine. The center is very, very, very hot, but it's so well insulated that it doesn't heat up. And of course, if you break a light bulb, it cools off and it doesn't stay hot. The same thing if you lose the insulation in a fusion machine.
Well, thank you, Bob, for rapid fire answers to rapid fire questions. This has been really helpful and really informative. It's now my pleasure and privilege to introduce Ryan Bucas. Ryan is someone who has had a lifelong interest in the practical application of physical principles, dating back to his home-built cyclotron that helped him win first place in the 1958 Westinghouse Science Talent Search. He then earned his BS at MIT, his PhD from Harvard, and served on the Harvard faculty for 12 years. Since then, he's been a successful biomedical entrepreneur many times over, with 80 publications and US and international patents to his credit. But it's as a conservationist who understands the urgency of the climate crisis that Ryan became an ardent citizen advocate for fusion energy, and in that passion, he's been haunting the halls of Congress and everywhere else talking fusion energy. And so with that, it's my pleasure to turn it over to Ryan.
There we go. Thanks very much, Brad. It's a real privilege to be here with this group and another forum to talk fusion. My white hair, ever seen in a photo line, causes the politician to say, uh-oh, the fusion guy is here again in line. But it's in fact a very special pleasure to be able to introduce Lori Trahan. Now, there's so much to say about Lori. I have to tell you that when I spoke to her earlier and I said, you know, Lori, there's so much that could be said about you in complimentary ways. There just isn't time enough in 3 minutes of introduction. And Lori said, well, take all the time you need. So I won't give in to that temptation. But the really important thing to realize about this, and that I've taken me a little time to realize, is that to talk science and talk practicalities and talk climate issues and CO2 is very important, fundamental. But in the end, it's the political process that makes things happen. And to have Lori there recognizing the climate problem, recognizing the capabilities of fusion to help in that solution is really, really important. Now, Lori came to Congress having served as the chief of staff, highest level chief of staff for Marty Meehan's as congressman. And she then getting into Congress on her own, you know, she said, I can do this, you know, I don't have to. Marty left, went off to education, but Lori said, let me do it, let me drive. And so got into Congress, and then almost immediately, it's astonishing to think that she got appointed by Nancy Pelosi to the senior committee of the House, the Energy and Commerce Committee, which has authority over essentially everything. She got into that, and then by 2020, she came in 2018, by 2020, she and Connor Lamb put in a major amendment to the energy bill, which was enormously broad, covering every aspect of bringing fusion energy into the national energy picture as soon as possible, including this very far-sighted approach of saying, let's have public-private partnerships, but let's make not only public-private partnerships in America to make authorization specifically to say, you could actually have partnerships with people outside America if that would make it happen sooner. So, and that was about, I don't know, that bill was about $400 million, which is now awaiting, it's approved, but awaiting appropriation there. And then moving forward, she's then been a major supporter of the fusion component in the Build Back Better, which amounts to about $800 million, relatively broad. And that, again, reflects her depth of interest and understanding of the place of fusion. It's probably worth also noting that Bob's facility in Devens just happens to be in her district. And yeah, there we go. You know, Ray for Massachusetts and Ray for her district. So, but she was in there before there was any plan to put it in a district. And that's really important too. She was there and backing things up, and then that's where it happened. So I think that I can't say, well, I could keep on going and keep on going. It's just terrific to have somebody of Lori's stature involved with us. And I'll invoke stature a little bit. If you stand next to Lori, you always have the impression that she's taller than you are. And you know, she was a volleyball champion, and if you could ever get her the ball, she could spike it over the net and make it happen and get the point. So that's where Lori stands right at the moment, as a tireless advocate for fusion, tireless advocate for the climate, tireless advocate for a future which includes all the options available, but focuses on fusion as something which is really necessary. You can't get there with what's on the table at the moment. We got to go forward. So Lori, take it away and tell us how you're going to make it happen in Washington. That's the hardest part. I mean, the physics is easy. The politics is really, really hard. And the physicists and me don't understand how that game is played at all well. Thank you, Lori.
Well, you understand better than most, Ryan. But first of all, thank you for that great introduction. I'm always so pleased when someone sort of takes the written bio and throws it away and just goes right off the cuff. And I'm grateful for your friendship, and particularly grateful for your support for fusion energy research at MIT and beyond, for educating so many of my colleagues here in the Congress, and for your relentless work to keep the promise of fusion at the forefront of our country's vision for a clean energy future. I'd also like to take a moment to thank everyone who is making today's discussion possible. Elizabeth Henry from the Environmental League of Massachusetts, Brad Campbell from the Conservation Law Foundation, and certainly my good friends Jane Hotchkiss and Wally Johnson from the Energy for the Common Good. Each of you have been absolutely essential in the push to treat climate change like the crisis we know it is. And I'm so grateful to you for convening all of us here today. So both the recent IPCC report and recent conference in Glasgow confirm what we have known for decades, that leaders around the world need to steward big solutions to the climate crisis now. In fact, Jane said it so eloquently at COP26 when she asserted, and I quote, "Fusion is the planet's moonshot to climate change solutions. We have to stop treating it like a scientific research project and treat it like a future commercial product," end quote. And in every conversation with Ryan, Jane, and Wally, they have advocated for the need for major investment from both the private and public sectors for fusion to finally make the leap from research and development to commercialization. I'm honored to have them as my constituents and represent an area of the country actively working on green energy technology with so much promise. I'd be remiss if I didn't also acknowledge Bob Mumgard and the leaders of Commonwealth Fusion Systems who are here as well today, and take a moment to congratulate you all on the incredible $1.8 billion Series B funding to construct, to commission and operate Spark. That's a monumental investment in your push to achieve commercialized fusion energy, and a testament to the work that you've all been doing for decades. So as the representative of the 3rd Congressional District here in Massachusetts, I have the unique honor of representing their new location, as Ryan said, in Devens, and advocating on their behalf as a member of the Energy and Commerce Committee. So I'll start by talking about those efforts. It's no secret that much of the debate over the past few months, as we've worked in Congress to advance Build Back Better, has focused on ways to reduce our nation's carbon emissions and combat the climate crisis, while also creating high quality jobs that pay family sustaining wages. But specifically, this historic legislation includes $500 billion in investment in climate change solution, the largest tranche of all the investments in the entire package. And although most of the focus has rightfully been on finding ways to make the transit sector more eco-friendly, to weatherize homes and other long overdue investments, it also sparked a conversation about what else we should be investing in to achieve those goals well into the future. For those of us in the Congressional Fusion Caucus, and I'm sure for many of you tuning in, the answer is pretty obvious. It's commercialized fusion energy. You all know better than most that the successful harnessing of fusion energy has long evaded researchers because of how difficult it is to reproduce the solar process in a confined space. But you also know that recent breakthroughs in fusion energy research have indicated that commercialized use of this virtually unlimited energy source is on the cusp of becoming a reality. And it's thanks to the substantial progress that's happening at facilities like Commonwealth Fusion Systems that we're seeing unprecedented interest and investment in resolving the challenges that remain. It's for that same reason that 2 years ago, the National Academy of Sciences recommended that the United States foster the research and development necessary for a pilot fusion plant. Of course, that doesn't happen without my colleagues in Congress understanding the value of that investment, which is exactly what my colleagues and I on the Congressional Fusion Caucus have been working to do. To that end, as Ryan mentioned, I partnered with Congressman Connor Lamb from Pennsylvania to introduce an amendment last fall to the Clean Energy Jobs and Innovation Act to expand fusion R&D across our nation's labs and universities and to facilitate greater private investment in the technology. Not only will our amendment help show the tremendous benefit of federal support, but it will also enable the United States to win the race to unlock the power of commercial fusion energy and the key role it stands to play in defeating the climate crisis. So I am pleased to report that this important provision was later made law as part of the Energy Act of 2020. However, our work is far from over because frankly, the urgency in this effort cannot be overstated. Those of us working hard on this issue recognize that we aren't the only country working to meet this challenge. In fact, many countries, including China, are pouring funding into a fusion power solution that could change energy production as we know it. And without additional federal investments in fusion energy now, the United States risks ceding our leadership to others, and we simply can't afford for that to happen. That's why the House version of the Build Back Better Act includes $885 million in fusion energy investments, including the $325 million I requested to carry out the milestone-based fusion energy development program created by my amendment. We must make sure that this provision survives negotiations with the Senate, and I'd ask that those of you who share my urgency around this issue to work with us and your contacts in the Senate to get this investment across the finish line. We have an incredible opportunity in front of us to initialize an industry capable of generating jobs for decades to come and to lead the world in developing a substantial new source of carbon-free electricity. All we need to do now is to take full advantage of that opportunity and maximize fusion energy's tremendous potential. So I want to thank you all again for taking the time to participate in this discussion, and just thank you for your commitment to unlocking the future of clean energy.
Thank you, Congressman. What are the key ways federal policy can help enable a breakthrough in fusion? And what are your top priorities in addition to funding?
Yeah, so look, fusion has the potential to create massive amounts of energy. We all know that, but the capital costs are also quite high, especially at this early stage of development. And I think this is where government investment can and must be helpful. The United States has a long history of investing in new technologies in the early stages of development, particularly before they reach a scale in which costs start to come down. The internet, GPS, heart monitors, solar panels. We have long acknowledged that government funds play an essential role in innovation. So that must be the priority when it comes to fusion as well. And that's the work that I and so many of the members on the Congressional Fusion Caucus are working to build consensus around. We recognize that by combining government investment with private capital, we'll be able to get this technology on the grid. So I think that those efforts are really yielding some progress. As I mentioned earlier, the last year, as part of the Consolidated Appropriation Act of 2021, Congressman Connor Lamb and I sponsored an amendment on fusion research. And in Build Back Better, the Build Back Better doesn't only include the $325 million that I already mentioned, but it actually includes a total of $885 million in fusion R&D spending. But it's also worth mentioning that the Biden administration is fully supportive of these investments. In fact, last week I had the chance to speak personally to Energy Secretary Granholm when she was in Massachusetts. Our office has been keeping her updated on the progress Commonwealth Fusion is making, and she couldn't agree more about the importance of getting those federal investments across the finish line to boost those efforts. I'll also add that every single Democrat in Congress recognizes that as we shift to clean energy alternatives, including commercialized fusion, we have an energy grid ready to get it to folks, right? In fact, since fusion plants don't require the sun to be out or the wind to be blowing, this means the energy from a fusion plant can be a trusted backup to other renewables, but only if we can efficiently move energy where it's needed. So I could I could go on and on. I think that's why we've built the progress into the Build Back Better Act, which does so much for our, for ensuring that our grid is reliable and resilient. These are investments that really matter. And I think that just by virtue of the fact that the biggest tranche of investment in Build Back Better has to do with combating climate change and making these types of investments, we're seeing Congress rally around the urgency of mitigating climate change. So I'm really hopeful, and I don't think I've been as hopeful about another moment in our history in terms of doing what's necessary with the urgency needed to combat climate change as I am today.
We heard a lot of questions today about the regulatory process and concerns about the regulatory process. What initiatives are you prioritizing in terms of how that issue is resolved at the NRC, Nuclear Regulatory Commission, and other agencies?
Yeah, so I think, the first thing that we have to focus on is making sure that the level of investment is there, that we're constantly, ensuring that we've captured the hearts and the minds of folks in terms of prioritizing this as an international issue. I think you've seen that reflected in some respects in the bipartisan infrastructure bill. We're also seeing it mostly with the prioritization of funds in Build Back Better. That is literally, I don't want to say that we're not thinking about the regulatory concerns that are going to follow, because we are. Those are, typically after we pass, major legislation like this, we do focus with a little bit more granularity around how that works, how that works in terms of its application, how that works in terms of agency rulemaking, how that filters down into everything that we need to do to make it work from a local, state, international level. So it's not that we're not there yet. I just think that we have been completely prioritizing and focused on. We're not done yet, right? We still have to make sure that all of this passes through the Senate, that these important investments are not stripped away in those negotiations, and that really is where the focus is. I do think that once we have a final bill, that we can all hold up, with pride and with leadership, that we're going to get to work on all of the regulatory issues that will emanate from those investments.
Brad, you're muted.
Sorry, we had a siren going by, so I had to mute. You've had to talk fusion with any number of your colleagues who are probably at a very early point in their understanding. And I'm just curious what kind of pushback you've gotten, and also, is there a concern so many energy issues fall into kind of a partisan mold, whether the support for fusion is bipartisan or not?
Yeah, so the Congressional Fusion Caucus is a bipartisan caucus. Certainly, we want to make sure that we're doing everything we can to get more Republican members on that caucus, and that continues. I sit on the bipartisan working group, which is an informal group of Republican and Democratic legislators. Where we meet on a weekly basis to figure out what are the issues that we can come together on, what are the new technologies that we can invest in, what are the workforce issues that we want to get out in front of. And I talk a lot about fusion in that group, and I recruit folks for the Congressional Fusion Caucus. This really is about evangelizing and educating members, and I think that is a really important piece that we all play a role in. I mean, I've obviously been, educated by Wally and by Jane and by Ryan and by so many folks, on this call today in terms of not just the potential, but then also all the other things that we're going to need to invest in, the magnets, plasma, building materials that are used in reactors. Can we move all or most of that supply chain here into the United States? Can we continue to create those jobs and the workforce issues? And I think as I do my very best here in Congress not to sort of fall into these partisan silos, to just talk about things that are of, shared importance. And I think fusion is one of those really incredible issues that once you start talking about it, once people kind of understand that this could solve all of our issues in terms of unlimited carbon-free energy, it really is just powerful. And I think in my most optimistic self feels as though it's one of those issues where we can come together and actually help rebuild the muscle on a bunch of other issues as well. So I do think that I try to stay away from sort of the partisan rhetoric that can creep into a lot of different issues. And I'll continue to do that. And what does that mean for all of us on this call? It means showing the value of private investment in this technology, showing that commercialization is not it's not a dream, it's here right now. Making sure that we educate our colleagues through Codels, through sessions, that legislative seminars that we either host in Washington or bring to their districts. And I think using all of those tools is really going to just foster in a level of priority that we want to see from on both sides of the aisle. And the Energy and Commerce Committee, there are times when folks move into their silos across, on either side of the aisle, but not on this one. So I think it's really important to just make sure that that doesn't creep in, and that we, make sure we have those hearings and those markups and those investments, and that they continue to be bipartisan.
Just as important, or perhaps more than the reaction of your colleagues in Congress, with one of the first pilot plants in your district, you're really on the front lines in terms of public response, public acceptance. What are you hearing from your constituents as they begin to understand the fact that this is essentially in their backyard?
Yeah, so to be, I think people are really excited, especially in Massachusetts, in the district that I represent. There's no question that when you go to town meetings, when you have these conversations, people are really, they're really concerned about the future of our planet. They're really concerned about the how we're going to pass the baton to our children, and where we are in that fight against climate change. We've lost a lot of ground, there's no question. We're making up for that ground by passing, once in a generation legislation like we are right now in this Congress. And I think what, this might not happen in every district across the country, but I think Massachusetts 3rd is unique. I'm reminded all the time when I drive through my district that the 45 acres in Devon's abuts, where we heard the shot around the world to start our American Revolution, miles from, where the Industrial Revolution began in the mills of Lowell and Lawrence. And I do think that ushering in this transformation in how we produce and distribute energy is actually going to be a point of pride for folks in the district that I represent. And I'm happy to talk to people across not just my district, but across Massachusetts, and certainly on the committee that I've got the privilege to sit on, that's happening right here. And we're all playing a role in that. The public investment that we hope to continue to provide, the private investment is really going to usher in a permanent solution to our climate change crisis. So I look forward to not only educating folks here on the Hill, but all the folks who are going to have the honor of calling the birth of fusion energy home in Massachusetts 3rd.
We have a number of comments praising you for your leadership on this issue and your support of federal funding. What do you see from the Hill perspective? What do you see as the biggest headwind, the biggest obstacle in terms of congressional support and policy support?
I think we don't sort of pass these policy prescriptions in a vacuum. And there are a lot of things I think at play right now, even as we, continue to deliver. Look, I'm astounded that there hasn't been more sort of acknowledgement that at a time when many folks have kind of given up on the effectiveness of government, we've actually had our most productive legislative session in generations, right? Passing the CARES Act, passing the American Rescue Plan, passing the Bipartisan Infrastructure Plan and Jobs Act, advancing Build Back Better. I mean, this is a really important time for our country as we combat a lot, right? Getting out of COVID, making investments to end the climate crisis, making sure that we get people back to work, making sure that, we recover quickly and that our economy is strong, and making sure that we continue our global leadership and the sense of pride that we have in that global leadership. There are a lot of headwinds, right, that confront us across all of those issues, right? We have a misinformation and disinformation problem in our country, right? There is a lot of dark patterns at play that are, dark to all of us, but we know that they're happening in terms of spreading, misinformation that can derail any logical and common sense policy prescription. We see it play out day in and day out. So I think it's important for all of us to play a role in ensuring that, one, we're all arbiters of truth. We're getting that out there. We're making sure that people are well informed, that they have good sources of information, making sure that, folks are sort of rooting their opinions in fact. And I think that right now is a big headwind that we're all confronting. You see that on local level, you see that at the state level. Of course, we're seeing it play out across the country. And so I do think that right now we are in this Congress, we are heads down in ensuring that we deliver. We lost a lot of ground. There's no question. You all know that better than possibly anybody else. We lost a lot of ground, but we're making up for that on how we handle decarbonizing our energy production, transportation sector, and our and so much more. So I think that is it's important that we constantly stay united, and we get that information out in terms of the progress that we're making, and that will definitely pave the way for us to make more of these investments, and make just more traction faster.
Thank you, Congresswoman. I know we have to let you go. Your team has asked for a quick picture before you go.
Great.
And, so if everyone can either smile or turn off your camera if you don't want to be on camera. We'll go 1, 2, 3. Snapshot.
Oh, great.
Thank you so much, Congresswoman.
Thank you so much. I so appreciate seeing you all and being a part of this conversation. There's no question that this is a busy time in Washington. I wish I could spend more time, but as you can imagine, we've got a lot to finish before the end of the year. So thanks again, everyone. Take care.
Thank you, Congresswoman. And thanks to everyone who was able to participate today. This has been a great dialogue and discussion. I really appreciate the questions. As just about everybody on this call recognizes, and as the most recent UN report on the climate crisis reflects, we are truly at a code red for humanity. And that puts this technology in a certain context, as does today's reporting by David Abel in the Boston Globe, where 2 key strategies for decarbonizing the New England energy system have foundered despite the best efforts of policymakers and advocates. And so we truly are in a position where we can't afford not to invest and pursue research in technologies that could potentially expand the climate solution set. Do we know if this is going to be the breakthrough technology? Not yet. But it's not too early to begin the dialogue about the many questions that are raised today, from how this is going to be regulated to what measures we need to inform the public and address the siting issues and other complexities that will emerge as this technology develops. So thank you for joining. I hope this is the beginning of an ongoing dialogue, and I'm grateful to ELM and Elizabeth for leading this effort.
Thank you, Brad. I'm also grateful to you for being my co-host, and to all of our speakers today, and to all of our attendees. Thank you so much for coming. We will follow up with an email that includes our thank you and a link to the recording. You're welcome to share the recording with colleagues. And as Brad indicated, I hope that this is the first of what can become just a loose series of educational opportunities for New England stakeholders on fusion. And we'll be reflecting after this call on what the next steps might look like. If you have ideas or feedback for us about what might be helpful, what you'd like to learn more about, I know I would welcome that feedback, and as would Brad and any of the other speakers on the call. So please don't hesitate to reach out. With that, I think we'll say thank you and have a great afternoon.